So yeah, Greg kind of threw out some different topics, and I decided to speak on these things. And it's a lot to pack into 15 minutes, so fasten your seatbelts, because here we go. Yeah, I've done 3 projects now. I'm about to do my 4th one. So the caveat that I want to make is that I haven't got this figured out. There's still a lot of stuff in here that's still work in progress, very much work in progress. Some of the things you'll see I thought were really great ideas, some of them not so good ideas, and you know, some things are going to have to go back to the drawing board. But I'm happy to share those experiences with you, and here we go. So part 1. Here we go. This is from my recent build, a new construction. This is the Sandwell build. So I want to run you through a high-performance wall, an R42 wall. So this is the wall in its inception phase. This is where the sperm enters the egg, I suppose, and fertilizes it, and you have all of a sudden the beginnings of a high-performance wall. What a great analogy. Somebody writing that down. I want to use that. So you have basically a 2x4 structural wall, and what you can see is plywood sheathing on it. Now this plywood sheathing forms part of the air barrier. The air barrier in this particular wall is designed to be in the middle of the wall assembly so that the sheathing stays warm in cold weather. You can see the window bucks are there for spanning through the larger wall that is to come. This is a side view of the floor platform. The floor platform is sitting about a third of the way onto the foundation wall. Typically it would be lined up with the edge, but this is the structural wall. There's some bearing left on there for the wall to come, which is not a structural wall, it's just holding up insulation. Here it is in progress. These are sleepers that are going against the wall now that are going to create cells, basically. The plan is to insulate the outside wall with cellulose insulation. And cellulose, though I have limited experience, I have figured out it likes to be installed in cells rather than one big open wall cavity. So this is the next phase, a 2x6 wall that is now going up in front of it. So now you have a 2x4 wall on one side, you have the air barrier, and now you have about an 8.5-inch cavity that's in the process of being constructed on the outbound side of the air barrier. This is good old 10-test sheeting that's being applied to the outside now. Its main job is going to be to hold in the cellulose. There it is again with the windows installed. And in between each of these cells, you can kind of see here, this black material is strips of the same type of sheathing to create cells in between the walls, because there was a little bit of a gap, about a 2.5-inch gap between this 2x6 and the sleeper against the wall. And this is what it kind of looked like. By the time the installation crew showed up, all the building wrap was on the wall, and the strapping, all of that, hopefully to prevent the 10-test sheeting from busting out once the cellulose got installed. One thing to make a note of here is your choice of building wrap is important here. If you're trying to build a wall that has drawing potential, you want to have the materials kind of not short-circuit each other. So the sheathing in behind there has a permeating of R35, highly permeable in the event that any moisture should get into the cellulose and it can dry to the outside. The Tyvek actually is a lot more permeable than Typar, like about 4 or 5 times as much so. So it was the right choice in this particular case. This is what the building looks like when it was with its tuxedo on. Now this is the insulation going into the inside of the outer wall, and it was installed from the inside. And there's not a lot of contractors around that have experience with insulating deep walls. This is something, I guess, if we're trying to push the envelope, so to speak, where we design these things and we make plans to execute them, but there isn't necessarily the knowledge out there in the trade community to be able to give us the type of things that we need. So this was a very good lesson here. So the idea was to install the cellulose into the middle of the wall, and it would fill top and bottom to an even density. As it turns out, I thought that little gaps didn't really matter. This isn't a blowout. This is just a small gap, probably smaller than a business card, where all of a sudden the cellulose started spilling out because we just hadn't bothered to fill that one little corner. I figured, it's going to bunch up and plug it up, and it didn't work out that way. So not a lot of this happened, but it's actually more liquid than what I thought it was going to be. The idea was to drill holes around the building and insulate top and bottom. When we did some quality control checks, courtesy of our good friends at the Blue-Green Group here, we realized that we weren't getting proper densities at the top and bottom of the wall. So now we had to drill all around the building again, top and bottom, so that we could inject more cellulose into the wall and then apply air sealing tape to the Swiss cheese that it had become. And then finally a layer of bats on the inside. So the total combined value of that is R14 bat plus about an R28 wall cavity gives you R42. all of the structural elements are over-insulated by the cellulose on the outside. So the thermal bridging issue is very well addressed with this particular design. It would have been easier in retrospect to probably use some sort of I-joist, and there's reasons why I didn't do that, which I'd be happy to discuss with you later on. The blower door test came in very good. The air sealing details worked really, really well. So it was partially an execution and partially a design issue. The building was sort of designed to simplify air sealing. It was always forefront in the mind of the project, and one of the major targets, one of the objectives was to get us a very, very tight enclosure. Here's where we kind of came in at 0.3, and this is passive house, and this is sort of like 10 energy to 6.5. There's your 1.5, just to put things in graphical proportion. Actually, could have left that slide out. Next, I want to talk a little bit about mini split heat pumps. It's kind of like a variety show. You had the juggler, and now I'm going to play the trumpet for a few minutes, and then we're going to look at something else. So, fact and fictions. A single head ductless conditions the whole house. This is just not true. It doesn't work. We know that now. The theory was that it could, but it actually doesn't work. I don't even know if it works in Germany where they say it works. So you do need a backup system, and a multi-head system kind of solves the problem, but now you're getting into a costly HVAC system. And this is one of the challenges that we need to overcome. The hope is, we're building houses that we don't need a furnace anymore. Well, we still need some sort of mechanical system. We still need heating and cooling. And how do you do it really cost effectively? I don't have the answer yet. I don't think anybody does just yet. This is a sort of a little case study kind of on my own residence. This is a retrofit, a deep energy retrofit I did in 2010. My wife and I moved back in 2011. So we've been running with these systems. And we have a single ductless mini split. This is the 1-ton unit. It's one of the more efficient, I think the MZ series, or whatever it is, it's one of the more, it's the SEER 20, it's not the SEER 26, it's the SEER 23 unit. This is the indoor air handler, which is located on the second floor, which I'll show you the floor plan coming up. And I want to combine it with my experience living in near passive house. And I think this pretty much says it all. I could probably finish the presentation right here, because it's like a cappuccino, folks. Foamy, a bit sweet, delicious, and it's got a handle. No, I should have written these jokes out better. It's got a spoon. I forgot to put the spoon. This is the house before. It was a 1957 bungalow, solid brick construction, 1,800 square feet of heated space up and down. This is it post-retrofit now. It's oriented southeast to northwest kind of thing.
You turned it?
What's that?
Just kidding. You turned it?
Exactly. I've got broad overhang, so very good summer shading. This is taken on June 21st, so you can see that the shading, the passive shading works really, really well. A super insulated house like this is really airtight. It's like a thermos bottle with windows. If you have a large direct sun exposure, it's going to spike up very quickly. You're definitely going to generate a cooling load in the house. Now, interestingly enough, we all know that this is the sun's steepest angle, but it's not the hottest time of the year. Hottest time of the year is actually probably a month out, July 21st. So by July 21st, this sun line has moved up another foot, at least up the window. So there's morning, probably a couple of hours anyways, where there's indirect or sharp angle, and then eventually perpendicular angle sunlight coming in, and it can spike up quite a bit. This is it in the wintertime now. The sun just washes right through the house very nicely and right up against the back wall. So we have pretty decent solar access. The house is super comfortable. On a cold winter day, the heating system won't come on until late in the afternoon if it's a clear day. There's excellent thermal comfort in all 4 seasons. Again, this is my actual experience of living in this house for 3 years now. Very little temperature variation from floor to floor, and also from within floor. So from one end of the house to another, there's very good temperature uniformity. The relative humidity is very good. It's in the summertime, it's probably in the 55 to 60% range, and in the wintertime, it's probably 45 to 50. And that's without any mechanical intervention. That's just a natural state of affairs. There is an ERV that brings in fresh air 24/7. In addition to these mini split system, I have a couple of zones of electric baseboard heating, and this is the thermostat that I have it hooked up to. When I did this, I honestly did want to believe that the single point air handler was going to be able to cool and heat the whole house. definitely has the capacity. The magic, or the question is, was it going to be able to actually physically do that? And now I know that it won't. But this is my first floor plan here. So it's about 1,000 square feet of space, and I have a 1,000-watt heater right here. And this is the northwest side of the house. There's a 1,000-watt heater here and a 500-watt heater here in the bathroom. They both have thermostats, and this effectively maintains these temperatures, 20 degrees pretty much constantly throughout. There's no baseboard heater anywhere else. This bedroom gets a little cool, and this corner of the house gets a little bit cooler, maybe 19.5 degrees. Nothing to complain about, although my mother manages to complain about it every time she comes over. It's good, it keeps her visits really short. Yeah, and in the summertime, it's actually pretty much about 23 degrees, and I'll get into that more in a second. This is the second floor. Now this is where the air handler is located, kind of in this mezzanine level on the second floor here. And I have a T there. There isn't really a thermostat. There's just a handheld. Remote that you set the temperature with. And I found it to be inaccurate. I don't know if anybody else has any mini split systems, but I don't find it very accurate at all. It doesn't matter. You just adjust accordingly. So in the winter time, it keeps it very, very comfortable. 20, 19, 19. In this house, warmer than that, it's too hot to sleep. I find it, if it goes up beyond that, it's just a little bit uncomfortable to sleep. There's a very comfortable sleeping temperature. In the summertime, this unit easily cools the entire house. It kind of spills the cool air out on the top floor, and it just slowly permeates throughout the entire house. These are the temperatures in the summertime, 22, 21, 22. Now, we've installed ceiling fans in here to move the air about. Before the ceiling fans, it would probably go up to about 23. So the ceiling fan helps to move the cold air around the room a little bit more and increase the comfort level. 1 degree can make a big difference between not sleeping and sleeping. And this has made a big difference. The ceiling fans were added in about a year later. In the basement, we keep the door to the basement closed. There's no cold air from the AC that spills into the basement. There's a very comfortable basement. I think that's always a challenge with a traditional heating system is, it can be 37 degrees and humid outside, but to go into the basement of the house, you have to put on your tracksuit because it's really freezing cold in the basement. So this house doesn't have that issue. And this is a typical temperature profile it's pretty much 20, 19, 18. It's a little bit cooler. It's a mechanical room. I've got some HVAC stuff happening. Here's a ground loop that refrigerates things a little bit. When I insulate the pipes, it probably won't happen as much. And in the summertime, it's very steady, 21 degrees throughout the whole basement. Last thing I want to just comment on is I actually measure my energy usage. So I actually tell you exactly how many kilowatt hours we use for heating and cooling. I have this system called TED, which is connected to my electrical panel. It measures 4 circuits. And this is sort of the control board. It's web-based, so I can see that here, obviously nothing's going on. But it'll tell me how many watts the systems are drawing. I can look at them, all 4 circuits at the same time or individually. And it gives me kind of a breakdown of how many since midnight, how many per month, et cetera, et cetera. It also over here tells you what your peak usage has been, which is always good to check against how you've sized your heating system. On the history tab, there's a breakdown of month history, day history, hour history of all the different data, so you can see, compare every day of the week. Again, by selecting up here, I can go with just the mini split or the baseboard heater circuits. This is what the months look like over the last 2 years. I don't want to go over my time, so I'm just going to keep going along here. This is just a graphical thing. There's a number of different options. You can see the minute by minute, hour by hour. This is a couple of days in January 14. I just wanted to point out, you can see how there's a dip here on the weekends, and that's because we do our laundry on weekends. And basically 100% of the energy from our laundry operations gets recycled inside the house. We have a condensing dryer, which basically discharges warm, hot, dry air into the house, and basically gives the heating system a bit of a break. There it is right there. We also have a recirculating range hood, which again keeps the conditioned air inside the house. It doesn't depressurize the house. This is a graphical representation of my actual annual usage breakdown for 2013. This is the energy usage by circuit. So the red is the Mitsubishi mini split in heating mode. So you can see that the basement was the biggest draw, and then the bathroom on the main floor. The bathroom on the main floor is also tied to a little baseboard heater in the basement. I forgot to show, in the basement, there's a 1500-watt heater that heats the basement. And this is the dining room one. So this actually adds up to less than 10% of the entire heat. It only works out to about 8% of the total heat or total energy for heating. This system has enough capacity to heat the entire house, but it just doesn't work. The heating is dispensed on the second floor and it does not redistribute throughout the house. It just gets too hot and we have to turn it off. And this is the actual breakdown for 2013. The entire electricity cost for the entire house was $1,370. Just over 10,000 kilowatt hours. Just under 3,000 kilowatt hours is the heating portion. At 14 cents a kilowatt hour, that works out to $400 for the entire year. And that's all delivery charges in. 14 seems high, 14 cents a kilowatt, because I'm really good at not using electricity on peak. The thing is, by the time you add in the delivery charges, it starts to get up there. Also, you know, if you actually use less, you're amortizing over fewer kilowatt hours, and it doesn't look as good. So, anyway, so that's my average cost, 13 cents a kilowatt, and that's last year. That's all for all 2013. Last winter, we probably paid closer to about $525 for the whole heating season, and that again is like 92% on electric baseboard heaters, which is the most expensive way to heat a house. So, lesson learned, I would probably have installed a ductless head in the basement and a bigger system that would offset a lot of the heat that is going on. And I'm thinking of using this as my company logo now, because it got such a huge, phenomenal response from the room that I'm going to use it as my company logo now. And that's it. I could probably go on for another 30 seconds for this. I think is what I have, but I won't. So thank you.